Greetings, my pooligans! Chewy of the Manipool here again to do the introduction. This is the second part of the James Webb Space Telescope appreciation stream that Cluze and I did. I'm very sorry it's taken me so long to get this out, but life and a somewhat bizarre mystery illness kind of got in the way, because of course they did. But if you haven't seen part one, then I highly recommend you watch it first, because that one set the groundwork for what came before the JWST, and you can find a link in the description, or it's up in the corner of the screen right now. So in this video, we're discussing the telescope itself. Where is it? Why does it look like a big honeycomb thing? What's with the spikes in all the images? And why did we spend so much to make it? We'll answer all these and more right now. So take a deep breath, because this is the deep end. Dum 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 jam. Yeah.
Almost immediately after Hubble was launched, like almost immediately, plans began for what became the JWST. At the time, it was called the Next Generation Space Telescope, which personally, I love that name, but it was also the 90s, so Star Trek The Next Generation was totally a thing. But I would have gone ahead and kept it that way as far as names go. But
yeah, you would have.
So JWST, they started that in the 90s. So it has been under development, not quite active construction, but under development now for we're pushing 2.5 decades, nearly 30 years that they've been trying to make JWST happen. JWST is a different instrument, though. It's not just a souped up Hubble. It's not just a Hubble with a bigger mirror. It's meant to investigate things that Hubble cannot. So you can think of it as a complement to the Hubble. Okay. It is meant to see light that is redder than the Hubble can. It's meant to see infrared light. But the choice to go infrared, it can be kind of a head scratcher. Why would you look in infrared? Well, remember, I said the universe is expanding, and the further away something is, the faster it's moving away from us, the more redshift it is. So the redder the light is for stuff that's far away. Now, another thing you need to keep in mind, astronomy is the ultimate archaeology. Because the further away you're looking, the further back in time you're looking. Because light is fast, but light is not infinitely fast. It takes time for light to get to us. And later we're going to be talking about some distances in a unit called a light year. And a light year sounds like a time, but it is not. It is the distance light travels in 1 year. So you can think of it, if you had a ship that was moving at the speed of light, and you flew for 1 year, that's how far you would get, is 1 light year. So it's a wicked large distance.
That's just under 6 trillion miles.
Yes.
Is a light year. It's 5.6, something like that, trillion.
Which those numbers start to get big, like real fast. And they
Yeah.
start to get to be numbers that don't really make any sense anymore if you give them in kilometers or miles. So it's why we switch to something like light years.
Yeah,
to
like,
give you
because
a better
1
sense.
light year is, what's trillion? 10 to the...
Billion is 9th, trillion
So
should be 12.
It'd be 12th, yeah. So
Yeah.
if you are talking in distances, a brain can't really comprehend something times 10 to the 12th. That's a 1 with 12 zeros. Like, our brains go, okay.
Yeah, the human mind was not really meant to. It wasn't designed to really think about numbers that big. As Pinball Witch asks in the chat there, the nearest star to the sun is about 4 light years away. So about 4 years traveling at the speed of light is the closest star to the sun. So space is, again, stupendously big. I mean, that's basically next door, and it's still like really far away. Yeah. Okay, so... JWST, we want it to see in the infrared, but the problem with that is, well, one of the problems with that is, if you want good resolution, your mirror has to be bigger the redder your wavelength. So we can't get away, if we want the same resolution that Hubble has, we can't have a mirror that's as big as Hubble's. It's got to be bigger than that, since we're looking in the red. Also, anything that's warm gives off heat, which is infrared light. So when we design an instrument for the infrared, we have to get it away from any sources that are warm. Sources like, the Earth and the moon. So let's take a look at a comparison between Hubble's mirror and, that's coming next. Let's take a look at where we're going to stick it. Let's take a look at where JWST's orbit is.
Yeah. Now, remember, this picture of the Hubble, I'm pretty sure is a photograph. And
yes.
it is, it's just above us. It's in near Earth orbit. It's just right up there. Okay? I have to click over here before this works. There we go.
So instead of near Earth orbit, for an infrared instrument, we've got to get it well away from the Earth because the Earth glows because it's warm. Heck, the moon glows because it's warmer, at least the half towards the sun is. So the JWST is stuck well out away from Earth at an orbit of about 1.5 million kilometers away from Earth at a thing called a Lagrange point. Now, Lagrange points, how can I describe? Lagrange points are weird. Mm-hmm. Lagrange points are special places in orbit. So, Chewy, if you could give me that next picture, I'll talk about Lagrange points. If you think about gravity as pulling things, it's not quite right, but it's close enough. If you think about gravity as pulling things, anytime you have more than one thing that's pulling, so for instance, suppose that we have the sun at the center here, and we've got the Earth orbiting around the sun, there are some special places where the gravity from the Earth and the gravity from the sun kind of interact to give you a nice place in space. Mm-hmm. One of them, the easiest one to understand, is the one labeled L1. That is Lagrange 1, and it's named after a mathematician, Lagrange. So if there are any Lagrange fans, hit us up in the chat. Yeah, there you go. The pull of the sun toward the sun and the pull of the Earth toward the Earth essentially balance each other at that point. So if I were to take, say, a space telescope and stick it at Lagrange 1, it would basically just kind of sit around Lagrange 1 pretty much forever. Yep. So that's the easy one to understand. Another one that's easy to understand is we could go with Lagrange 3, which is basically on the other side of the sun. The place that science fiction authors love to put in Earth 2, as if there's a clone Earth over on the other side of the sun. There isn't, by the way. We checked. There's totally no other Earth over there.
What is that called in Marvel Comics? Counter Earth, I think? I think that's right.
I think so.
Yeah.
I think so. So there's nothing over there. Sorry. But if we stuck something over there, it would orbit the sun pretty much just like the Earth does. It would just be nice and stable. There are also some other spots in the orbit around the sun at L4 and L5 that both also work pretty well. The pull from the Earth in one way and the pull from the sun in the other way basically hold something there nicely. So as the Earth goes around, they'll just stay there. If you're familiar with the Trojan asteroids in Jupiter's orbit, they're at those Lagrange points. But there's this other one, L2, outside of Earth's orbit. And L2, usually at this point, people are kind of scratching their heads. Like, L2 doesn't make any sense. Because if the sun's pulling in and Earth's pulling in, shouldn't that thing just be pulled in? And what you're missing is that they're orbiting. The Earth is going around the sun. If we stick something out at Lagrange 2, it's also going around the sun. And even though its orbit is bigger than Earth's orbit, because of the extra pull from Earth, the amount of time that it takes to go around is exactly the same as the amount of time that it takes Earth to go around. Okay? It's a little weird and complex, but you're just going to have to trust me. We don't have time to go into the details of the math here. But basically, it's a stable point.
The math works out is all you need to know.
Yeah. So we decided to stick the JWST out at Lagrange Point 2. And it doesn't sit exactly at Lagrange Point 2. It orbits around Lagrange Point 2, so it moves around a little bit out there. But we had to stick it out there to get it away from the heat from both the Earth and the moon. There were other things about its design that were important. So, like I said, the mirror had to be bigger. So I think we've got a picture of a comparison between the Hubble's mirror and the JWST's mirror. And so you'll see that it is substantially larger than the Hubble's mirror was. You might also notice some other weirdness about it, and that is it's not really a perfect circle. So here we have a typical human being We've got the Hubble primary mirror next to it. That's about 2.5 meters in diameter. And then next to it, we've got the JWST primary mirror, which is about 6.5 meters in diameter. Meters about 3 feet. So if you want to do that conversion in your head, feel free. But the JWST mirror is also not a single mirror. It's multiple mirrors that all interlock with each other. And why might you do that? Well, building a 2.5 meter mirror, we can totally do that, no problem. Building a 6.5 meter mirror, that's a lot more tricky, and it's really hard to do. And for a reason I'll explain in a minute, we don't really want that mirror to be a single solid piece because the JWST can't be launched in a space shuttle. Number one, because we don't have any anymore. And number two, it won't fit. So it has to be put on a rocket. But if you're putting it on a rocket, there's a size to the payload that you can use. So the JWST mirror actually folds. So looking at it here, kind of the left and right row, the far left and the far right, they actually folded behind the primary mirror when it was launched, and they unfolded on the way out there. In fact, the whole JWST itself kind of folded up like origami and then was launched on a rocket and then unfolded itself on its way out on its journey to 1.4 or 1.5 million kilometers out there. Now, like I said, you need your mirror to be bigger if you're going to do the near infrared. And the bigger your mirror, the better resolution you're going to get with that instrument. I'll also note a question that has come up. Why is the JWST mirror gold? And first of all, it's not completely made of gold. The mirrors itself, like the glass of the mirrors, are actually made of beryllium to make them really, really light and very strong. But they are coated with a very thin coating of gold. It's actual gold that's on there. And you do that because gold reflects infrared light really, really well. So that was also a choice that was made.
You're saying there's gold in them, though, L2s?
There is, but a tiny amount. I mean, you're talking a couple of atoms thick across the surface of that mirror. So it's not worth flying out there to try and steal the gold, the precious, precious gold that is in the JWST.
Nobody tell Yosemite Sam.
Bigger mirror gets you better resolution. So I think we have a comparison of 3 different infrared instruments to get you an idea of what kind of a change in resolution we're talking if you look at infrared instruments. And so some earlier infrared instruments, WISE and Spitzer, those were both smaller instruments that were trying to do infrared astronomy. And so we have 3 different images of the exact same point in space. And you can see with the WISE instrument, you can see the bright sources, they're the big blobs, but it's really hard to make out any detail in the background. Later, we had Spitzer, the Spitzer Space Telescope, and that was a revolution in resolution in infrared astronomy, and so it is a much, much better image that we get there. But then we go to the JWST, so our latest iteration of infrared telescope, and you can see we're looking at the same place, but now we can actually see a lot of the detail in the gas that's in the background. We can make out a lot more sources that are in the background. So it's a huge step up in our capabilities in infrared.
WISE was the NES, Spitzer was the PS1, JWST is the PS5.
Yeah, I was gonna say we're definitely going to PS5 here.
Yeah. There's no comparison here.
So fantastic step up, but to get that, to do that, you had to have a bigger mirror, which is why we built it. Pretty much as big as we could fit on the rocket is what it came down to. When we did that. Now, you'll notice something kind of interesting in this image. If you look at the bright star kind of near the center and up a little in the center of that JWST image, you can see this really weird like 8-pointed star to it. You can see these like lines that are sticking off the sides. That's what's known as a diffraction spike. And so to explain a diffraction spike, you have to understand a little bit about optics and a little bit about how telescopes work. So we've looked at what the primary mirror is on the telescope, and that's where the light first hits. That's why we call it the primary. But then it bounces off of that mirror and it hits the secondary mirror, another mirror that's held there, and then it bounces through the hole in the hexagons. And the instruments are through that hole in the hexagons. But something has to hold on to that secondary mirror. So anytime you have like a thin support structure blocking part of your light path, you're going to get these diffraction spikes. So here's a comparison of the Hubble Space Telescope diffraction spikes to the James Webb Space Telescope diffraction spikes. And again, this is because of this thin support structure that's holding that secondary mirror there. Now, on the JWST, there's actually two reasons for the diffraction spikes. There are three supports, and you can see them in this little inset in this picture here. There are three little supports that are holding that secondary mirror, but you also get some diffraction spikes from the hexagons of the mirror itself. Because it's not perfectly round, you will get some slight diffraction spikes. Each of those things generates a set of 6 diffraction spikes. But you're seeing 8 in this image. Well, we tried to arrange things so that some of those diffraction spikes would fall on top of each other, as many of them as could, essentially. And so if you go to the next image for us, you'll see where those diffraction spikes overlap with each other. Yeah, so there you go. So we get this set of diffraction spikes on the left that we're showing in red in that little inset. Those come from the support for the secondary mirror. And then because of the hexagonal structure of the telescope itself, we get these ones that are shown in gold. And we lined up as many as we could. And so instead of ending up with 6 or 12, if you saw all of them, you end up with 8, the way it was done. And I've seen some criticism from people that like, why do you bother with those diffraction spikes? Why don't you clean those up in data processing? Well, okay, you can clean them up in data processing. What you can do is you can take an image and put the spikes in one part of the image, and then you could rotate the telescope and take another image so the diffraction spikes fall in another part of the image. Combine those two images and try and eliminate where those lines are. The problem with that is you've just degraded some of your data everywhere where you took out diffraction spikes.
Yep.
So instead, what they try to do is make it so the diffraction spikes don't run into anything they're trying to look at. And if they do, they'll rotate the instrument. But if they don't, they're not going to worry about it.
Yeah.
Okay. So why do the struts make 6 spikes instead of only having... Okay. Well, technically, the struts are not making 6 spikes. They're making 3 lines that all overlap in the middle. So each strut makes one line. So one strut makes one line, one strut makes another, one strut makes another, but they all cross in the middle. So it's not really 8, it's really 4, but it looks like an 8-pointed star, so it tends to get referred to as an 8-pointed star.
Yeah.
So that's the idea of those diffraction spikes and why they exist. Now, one thing
most
is
of
that now
the JWST images, the two on the side, at least the ones we've seen thus far, the two on the side are so small as to be not there, which is why you see most people talk about it being 6-pointed as opposed to Hubble's 4.
It's interesting. People who don't work on the JWST call them 6-pointed. People who do work on the JWST always call them 8.
Yeah.
At least from what I've seen in their press conferences. So the neat thing is, now that you know this, you can instantly tell when an observation was taken with the JWST. Because if there's a bright source, you'll see the 8-pointed star. If it was taken with the Hubble, you'll see the 4-pointed star. And you'll only see it on the bright sources. Technically, it's there on all sources, but it's so far down below detection thresholds on the faint sources that you just don't see them at all.
Yeah.
But on the bright ones, you definitely see them. And by the way, now that you know that fact, in general, if you see an object with a diffraction spike in a JWST image, it is probably a star in the nearby universe, so probably part of our own Milky Way galaxy, because only bright things will make these diffraction spikes. Okay.
We will have one notable example, notable exception. That's the word. Thank you. Coming up shortly. Ouch.
So JWST cost a bundle of money to make, like an absolute astonishing amount of money to make. It cost $10 billion to make the JWST.
Yep.
But we had to build this. We had to build this incredibly complex structure that could fold and unfold, and we had to launch it out beyond the moon's orbit. And there was a lot that went into that. So if you think about this structure collapsing in on itself, parts of the mirror fold behind, the struts that are supporting the secondary hanging out here in the front, that folds down. The accordion structure underneath, this what looks like aluminum foil underneath, a lot of people are really confused about this. Like, what is this? Why is this there? This is a heat shield. And it's multiple
it's there
layers.
so Lego can sell Lego versions. That's the only reason.
Well, I believe they are making a Lego JWST, and I will be buying one, I assure you. I do have a Lego Hubble. I should have brought it with me for this stream, but I do have a Lego Hubble. This accordion structure is a series of heat shields that protect it from the sun. So although this image, which is a rendering, it's not actually how the JWST really looks. I mean, it's very, very close. I mean, it's a perfect rendering of it. But you see how the one side is all lit up, the side with the mirror? Yeah, we don't actually let that side ever point toward the sun. The sun is always underneath the heat shield. It's always behind the heat shield to try and...
Because it's the source of heat.
Yeah, because we want to block all of that heat. So, in fact, the JWST cannot look at the entire sky at any given time. It can only look on the side of the sky that's away from the sun. And if you want to see the stuff on the other side of the sky, you have to wait for the JWST to move in its orbit as it goes around with the Earth to actually look at those parts of the sky. So it was launched eventually after many, many delays and many budget increases. It was launched on December the 25th of 2021. So it was launched on Christmas Day of 2021.
Wait a minute. Should we mention the budget?
I was going to right after I got out this sentence because it's a great sentence. Then began what is called the 30 Days of Terror, because the JWST had to go out to that Lagrange 2 point, and it had to unfold all of its pieces. There were literally something like 300 or 400 individual single points of failure that if any of them failed, this was a bust. It was done. But it worked. We're going to talk more about those in just a second. But to put things into perspective, the JWST cost $10 billion over 30 years. Mm-hmm. The budget for the Department of Defense of these United States of America is in excess of $700 billion for 1 year. So although $10 billion sounds like a lot of money to you or me, in the grand scheme of things of governmental budgets, it's not that bad, right? If you want to build a single aircraft carrier, that's like $13 billion just for one aircraft carrier. There are planes that our military uses that are, tens of millions of dollars a piece. So $10 billion over 30 years really is not that bad. It's a bargain for what this thing actually does. By the way, while
virtually nothing.
While I was talking about that, my wife did bring me my Lego Hubble. So
hey,
here's my Lego Hubble. It is to the correct scale for a Lego space shuttle that I have. You can actually fold it up and put it inside of the Lego space shuttle.
Dude, no way.
It's kind of a pain because you have to take you've got to take the solar panels off because of course they would have been folded up when it was inside of the shuttle bay. So
that's really cool.
Yeah, so there's my Hubble. Like I said, as soon as the JWST model is available, I will totally be buying that and putting it together because I don't know if you know this, kind of a science dork. Okay, so can you bring up the 30 Days of Terror?
There was a question in the chat.
Oh, sure.
Said how thick is the structure? Like the heat shield? Do we
the heat shield is incredibly thin. To call it like aluminum foil is actually very, very accurate. And it was sandwiched together and then rolled. So like each layer is its own like roll. And so it unrolled and then unaccordioned itself, if that makes sense.
Yeah. And so you don't need, when you've got something like, we'll call it aluminum foil, because of the way that it deals with, it dissipates heat, you don't actually need a lot of it for it to do exactly what we need it to do.
Yeah. If you know, like, if any of you have like a vacuum thermos, like one of those like nice travel mugs that you put coffee in In between the inner wall and the outer wall of your coffee mug is vacuum, because it's basically no air whatsoever, because that's a very good insulator. You can think of this accordion structure as being a layer of metal, vacuum, a layer of metal, vacuum. It's actually the best vacuum you could ever have because it's in space. So it is incredibly, incredibly good at keeping this instrument cool. All right, so if you could bring up our 30 Days of Terror graphic.
Yes, sir.
This is where I have a confession to make. I've been a professional astronomer for a while now. Most of my professional astronomy career, including much of grad school, came while the JWST was being developed and proposed and constructed and getting ready for launch. And during most of that time, I thought the JWST was a bad idea. I did not think it was going to work. It is an incredibly complex piece of machinery. Again, hundreds of points of failure that if they don't go right, you're basically screwed. And it was my worst fear imaginable that this thing would be launched, it would get partway there, something would get stuck or something would break and it simply wouldn't work, and we would have a $10 billion paperweight sitting out at Lagrange 2. This is not because I don't have faith in NASA. I do. They're very, very good at what they do. It's not that I was worried about the engineering or the design or anything like that. It's just that the Hubble was so close we could service it. And lots of things went wrong with Hubble. Lots of things had to be fixed with Hubble. This is a one-shot. You do not service the JWST. There is no way to get a spacecraft out there to service it and then come back. That is not a thing that is going to happen, at least not for the foreseeable future. So I really thought it was going to fail.
This is over 3 times as far away as the moon.
Yeah.
Like if you go to the moon and come back, you're still haven't traveled as much distance as it takes to get to the James Webb Space Telescope.
Exactly. And I have people all the time, when I'm like doing observing with the public, and they'll ask questions like, hey, can we point your telescope at the JWST? And the answer is, well, I can point it to where it is, but you're not going to see anything. This is a tiny, tiny little blip in space. You're not going to see a darn thing where that's at. Over the course of 30 days after it was launched, I watched with bated breath. I checked every day on the latest news as it made its way out. And there were certain mile points where it unfolded a piece or where it opened up a piece, and we all breathed a collective sigh of relief. And then it finally got out there and it started to take data. Now, it couldn't take data right away, because remember I said this thing had to get away from the heat of Earth. It itself was hot. It needed to cool off. It needed time for all of its instrumentation to come down to temperature, because it does have coolant on board. It does have propellant on board, which does mean that it has a finite lifetime. One really good thing, though, it was built originally with a 10-year service mission in mind. But they nailed the launch so perfectly that they conserved enough fuel that it should have enough fuel on board for maneuvering and pointing and attitude adjustments, all that kind of stuff, to last for 20 years. So there is a good chance that they doubled its lifespan just by being really, really good at math. So stay in school, kids. Math is super important, is what I'll say. So there it sits out there at Lagrange 2 with one side pointed toward the sun, keeping all that pesky heat away with its nice little heat shields. The other side, it can point and it can look at space. During this time, as they were cooling the instruments down, they were aligning the mirrors perfectly. And so there's a fantastic image you can find online that has a picture with 18 stars on it for the 18, I think it's 18 mirrors that are in it. And then another image where all of those stars are focused to a single point, because it's the same star 18 times, and then they focused it so that they're all pointed at the same spot. And that was a huge collective sigh of relief because everything was working. Now, I will say one thing that bears mentioning. It did get hit by something. Space is not completely empty. One of the mirrors has taken a nick from a micrometeorite careening through space, so a tiny little piece of rock or dust or something smacked into one of the mirrors, and so there's a little chip out of one of the mirrors. They expected this. They planned for that.
Yep.
Okay. They knew that over time the instrument would take some hits. It's a little unlucky that we got one so soon, but they were planning for it. It's totally fine. The images are still great. Supposedly, if you know where to look in the raw data, you can see a slight degradation of the image because of it, but you have to really know where to look. Okay, it's like one of those where you, it's a bit like you've got a new car, right? And the new car looks perfect, and then you get that one tiny chip in the paint. Okay, the rest of the car is totally fine. It totally functions. It's A-okay, but there's that one tiny chip that we all know about.
And there you have it. Now you know why it's way out there. You know what the different parts are for. You can instantly differentiate JWST images from Hubble images. And you know that it didn't actually cost much of anything. Oh, and you got to see Cluze's awesome Lego Hubble, which, let's be real, was worth the price of admission all by itself. So in the next video, we get into the stuff that everyone's been waiting for, the pretty pictures. This stream happened, originally, just a few days after the very first batch of images were revealed, and they were actually what inspired me to do this stream in the first place, because I wanted everyone to understand that they were looking at far, far more than just pretty space pictures. So, next episode, Cluze and I are going to go through each image, explain what it shows, and explain why each one is absolutely mind-blowing. Because they are. So that's it for this dip into the deep end. If you want to be sure to catch the next two parts, then you should subscribe to the channel. Obviously. And if you want to help out, then please, by all means, share this video with people to help me spread the word about the new channel. And of course, to support what I do, you can check out patreon.com/themanapool. I've been Chewy, waving and drowning, and I want to thank all you pooligans for joining me. And with luck, the third part will be up much, much more quickly, so I'll see you then.